Hello everyone, welcome to this course on software defined radio hands-on for communication system design. I am Professor Suraj Srivastav from the Department of Electrical Engineering at IIT Jodhpur, and in this next lecture we are going to see an introduction to MATLAB Simulink and supported SDRs. So first we will go through an introduction to MATLAB and Simulink. Now, what are MATLAB and Simulink? MATLAB and Simulink are industry standard platforms for modeling, simulation and implementation of communication and signal processing systems. So, these platforms MATLAB and Simulink not only used in academia for research, they are also used in industry for modeling, simulation and implementation of various communication systems and signal processing systems. In particular, MATLAB is a very powerful environment for numerical computation, algorithm development and data visualization, while Simulink is a graphical environment for modeling, simulation and analyzing systems using a block diagram based approach. And this is what extensively we will use. We will be mostly using Simulink for the communication system design and MATLAB for computation. So, this graphical environment makes Simulink an ideal system for communication system design. Together, MATLAB and Simulink enable a model based design workflow where engineers can seamlessly move from concept to the real world implementation. So, first thing is that we have to understand the theory, and then MATLAB and Simulink enable us to implement that theory from concept to real time implementation. We also use them for designing complex signal processing chains. One can test the algorithms under realistic channel conditions, and finally MATLAB and Simulink can also be used to verify system performance before deploying them in the hardware. The key toolboxes, we have already discussed this thing in the last lecture. The key toolboxes used for SDR hands-on program will be the communication toolbox. So, communication toolbox is mainly for modulation, coding, channel models and link level simulations. Then we have another toolbox which is the signal processing toolbox for time frequency analysis. Very frequently we will encounter where we want to do the time and frequency analysis, filtering and spectral measurements. So, for that we will use signal processing toolbox, and for real time DSP processing we will need DSP systems toolbox. So, these toolboxes you have to install during the MATLAB Simulink installation, and in addition we will also require Simulink support packages for SDR hardware when you want to integrate your model with the SDR devices. So, we had seen in the last lecture, we had seen 3 important packages. So, those packages will require for SDR based implementation. We will again see all these things. So, with this now let us move to the SDR. What is an SDR? So, SDR stands for software defined radio, and let us first look at what is radio. So, radio is the technology of sending information through air using electromagnetic waves. And a typical radio system has 3 components. One is the transmitter, which is used for transmitting the information. Then we have channel, which is in most of the cases it's wireless propagation. So, it's air or any other medium can also work as a channel. And then we have a receiver. So, receiver is used to capture the information and then recover the information. So, how was the conventional radios? So, in conventional radio, this entire system was implemented in hardware and these were hard coded. Now, what are the components of a typical radio system? So, we have mixers, filters, analog to digital converters, digital to analog converters. Then we will see modulators, demodulators, various signal processing algorithms, various channel coding schemes. All these are the component of a typical radio communication system. And when we say that a conventional radio used to be implemented in hardware and it was hard coded, that means the parameters of these components, for example mixer, ADC, DACs, modulator, demodulators, they cannot be changed. So, there was almost no flexibility in the conventional hardware based design radios. So, in terms of changing various parameters like carrier frequency, bandwidth, sampling rate which is associated with ADC, DACs, and then modulation, demodulation. For example, today you want to use BPSK, tomorrow you want to do QPSK with the same hardware system, it will not support it because the hardware radio is designed for the BPSK system. And similarly, various signal processing algorithms, coding schemes, etc. cannot be changed in a hardware hard-coded conventional radio systems. How does software-defined radio overcomes this? So in a software-defined radio, most of the implementation is in software or it is controlled through a software. So either you will see that most of the implementation part is in software, that design itself is done in software and the system works with most of the components as software, or those components which are in the form of hardware, they can be controlled through software. Now in this software defined radio, when we say radio, so radio part mainly represents the RF front end, which is in the form of a hardware. So RF front is the hardware in the software defined radio that converts the EM signal and digital samples. So for at the transmitter side, the digital samples are converted into the EM signals, and at the receiver side, the EM signal, the captured EM signal is converted back into the digital samples. So this part mainly is implemented in hardware. So although it is in hardware, but the important part here is that in a software defined radio system, this radio part can also be controlled through software. For example, changing the carrier frequency, changing the sampling rate or tuner gain can be adjusted from the software. So we will show you how this is done. So basically, when we have a software defined radio system, so the SDR device is connected to a MATLAB Simulink environment, and through MATLAB Simulink environment you can control various parameters. So this is about the radio part, but if you look at the other components, for example, modulation, demodulation, channel coding and various other signal processing algorithms, they are completely implemented in software. So that means you have a lot of flexibility. Today you want to design a system for Wi-Fi, same software defined radio can work for Wi-Fi system. Tomorrow you want to work on the same SDR for LTE system, you can implement an LTE system, because many of the software part, for example, modulation, coding, signal processing algorithms are completely implemented in software. There is nothing hard coded in this component. So this is the advantage of software defined radio. So in summary, the software defined radio SDR replaces traditional hardware specific radio components with flexible software based implementation. And one thing is very important to understand, that SDR is not an end product of the communication system. The end product has to become in the form of a ASIC, the application specific integrated circuit. But SDR enables us to prototype the system and test various wireless communication systems on the same hardware. So again, I will repeat this thing. SDR is not the end product of a wireless communication system. It is for prototyping and test various communication systems simply by changing the software. As I already mentioned, if you want to prototype a Wi-Fi system, you can implement a Wi-Fi system on the SDR. If you want to implement a 4G system, 5G system or any other advanced communication system, you can implement on the same SDR. So this is what SDR enables us. Now when we work in MATLAB Simulink environment, there are some SDRs which are highly supported by the MathWorks. One is USRP, which stands for Universal Software Radio Peripheral. This is a family from NI, ETUS Research, and this is widely used for research, prototyping and education. So this is one set of software defined radios. Many of you, if you go to your communication systems lab, then you will see some of these software defined radios. Another class is ADLM Pluto SDR from Analog Devices, which is a very compact, low cost and USB powered SDR, and this is ideal for academic experiments. Finally, we have this third class, which is RTL SDR, which is an affordable receiver useful for spectrum monitoring and receive only experiments. So this also we had already discussed in the last lecture, that RTL SDR is mainly for designing the receiver side experiments, but USRP and ADLM Pluto SDRs can be used for both transmitter and receiver. The typical cost of these SDR platforms are as follows. The USRPs starts from roughly 1.5 lakh to 2 lakh, and ADLM Pluto SDR, they are low cost, roughly in the range of below 50,000, 30 to 40,000. And RTL SDR is extremely low cost since it is only the receiver side. So this comes within the range of 10,000. So this is the typical range of SDRs. Now, how do we enable MATLAB and Simulink to connect through these SDRs and do the live experiments? So for this, MATLAB Simulink provide dedicated hardware support packages. We had briefly discussed this thing in the last lecture. So to enable these platforms, MATLAB has already provided some supporting packages which enable real-time communication between the Simulink or the MATLAB models which will be running on your computers with this SDR hardware, and this connection is done via Ethernet cable or USB cable. So I will show you some of these SDR examples, and using these interfaces we can transmit and receive live RF signals. One can perform the baseband signal processing such as the various signal processing algorithms, modulation, demodulation, channel coding, etc. And one can also gain valuable hands-on experience in wireless communication prototyping. So these are the advantages of SDR based platform when we use them using the MATLAB and Simulink. So as I mentioned, when you want to install the support packages for these SDRs, so in the MATLAB you have to go to the add-on tab, and in add-on tab if you search for this communication toolbox support package for USRP radio, you will get the required package and you have to install it. If you have the ADLM Pluto SDR, then you search for this communications toolbox support package for analog devices ADLM Pluto SDR radio. So you will get the installation package and you can install it, and similarly for the RTL SDR. Before moving to the next part, I will briefly show you how are these SDRs. So I have kept some of these SDRs. So this is the ADLM Pluto SDR with me, and as I mentioned, this SDR supports both TX and RX. So we have one for the TX, one port for the RX, and this is the ADLM Pluto SDR. This is the handheld SDR, as you can see. Similarly, I have another SDR which is the RTL SDR, and you see this is in the form of a USB dongle. So this is only receive SDR, so it can only receive the signal. There is no transmit port here, and you can connect this SDR with your computer using this USB cable. Similarly, we have another SDR which is the high-end SDR. This is the USRP. So this is the USRP B200 SDR. So you see here we have two ports. One is for both TX and RX, and other port can work as RX. So this can be used for both transmitter as well as for the receiver. And again, this B200 SDR can also be connected through your system via this USB cable. So in the USRP family, there are some additional SDRs. Some of you may find, for example, B210 or N320, N321 or any other high-end USRPs. So all of them can be connected through your computer via Ethernet port or via the USB cables. So if you have any of these SDRs in your lab, so you need to install the supporting packages for that particular SDR, and while installation, if you have SDR ready with you, then you can connect it with your computer and you can complete the installation. If you don't have the SDR, then you can skip the installation, the device configuration part, and you can proceed with designing the models. Now we would like to see what is the connection between the MATLAB Simulink and SDR environment, or how do we connect our MATLAB Simulink models, the models which we will design in MATLAB Simulink, with these SDRs. So this is a block diagram. This is a representation how we develop or how we prototype the wireless communication systems in SDR based environment. So let us suppose you want to transmit some signal MT. MT is your message signal. And let's talk about the analog communication. We'll begin with the analog communication. So MT is an analog message signal which you want to transmit, and we had seen in analog modulation we'll study amplitude modulation and frequency modulation. So for each of these waveforms, whether it's amplitude modulation or the frequency modulation, this ST represents the final waveform. So this is your AM or FM waveform, and this is the waveform which the SDR will transmit. And all of you have done some courses on communication systems, or if you haven't done, then we'll cover some of these things in the subsequent lectures. So each of these waveforms, AM, FM or any other digital modulation technique has a particular expression. That expression has to be transmitted from the antenna of the SDR. So ST represents the final, this is called passband waveform. This is the final passband waveform which the transmit SDR will transmit. Now, in order to generate this waveform ST from the transmit SDR, MATLAB Simulink model generates another equivalent, this is an equivalent complex baseband waveform for the corresponding signal. So, if you have a message signal MT and you want to generate, let us say, AM waveform for this corresponding to this, which SDR should transmit, then you have to generate an equivalent complex baseband representation which is called S tilde T. So, I am denoting it with S tilde T. S tilde T represents the equivalent complex baseband representation of the final waveform. And our MATLAB Simulink, which is running on the computer, that will generate this waveform. So, S tilde T will be generated using the MATLAB Simulink environment and our message signal is MT. And after that, this S tilde T will be given to the transmit SDR, which in our case may be the USRP or Pluto SDR. So, this complex waveform S tilde T will be given from the computer to the transmit SDR, and finally this transmit SDR will generate the waveform ST. So, once again let me just summarize this part. The message signal is MT, which you want to transmit through an amplitude modulation or FM modulation. So, you will generate an equivalent complex baseband representation of AM or FM waveform from the MATLAB, and this S tilde T is complex in nature. So, complex means it is a complex valued signal which has a real part and has an imaginary part. So, S tilde T is the complex waveform, and this waveform will be given to the transmit SDR. Transmit SDR will finally generate the final waveform AM or FM, which has to be transmitted over the air. So, the typical AM or FM expressions which you see in your textbooks, any of these standard textbook, this is your ST. So, we have to generate its equivalent complex baseband representation. That is what we will see throughout the course from the MATLAB Simulink. So, this is what we mentioned here. S tilde T is generated from MATLAB Simulink and sent to transmit SDR, and the transmit SDR generates the final waveform ST, which will be transmitted over the air via the TX antenna. Now, this waveform ST, which is the final AM, FM or any passband waveform, will be transmitted over the air. So, it will actually propagate through a real wireless channel, and this waveform ST is a real waveform. So, this is a real valued waveform, and as I mentioned, this is possibly complex. For some of the waveforms, this S tilde T can be real, but in general S tilde T will be a complex valued waveform, ST will be a real valued waveform. And this looks obvious because if a waveform has to travel through the real environment, it has to be real in nature. Now, this waveform ST will be transmitted over the air and it will propagate through the real wireless channel and receiver SDR at the antenna. So, this is the real valued received waveform, and this RT will be converted into an equivalent complex valued waveform which is R tilde T. So, this is the job of receive SDR. So, the receive SDR receives the real passband waveform RT from the air via antenna, and then it generates an equivalent complex value. So, this R tilde T is again a complex valued waveform. So, this is a complex valued waveform, and this complex valued waveform is given to the MATLAB Simulink model, which is running on our host computer, and by using our signal processing algorithms, modulation, demodulation, blocks implemented in MATLAB Simulink, we recover the message signal MT back. So M hat T represents the estimate or the recovered message signal MT. So this is an end-to-end system which shows you how MATLAB Simulink and SDRs interact. So MATLAB and Simulink, they run on a host computer which is connected to the transmit SDR through a USB. So this connection is through this connection, or this connection is through a USB cable or Ethernet cable. So this Ethernet cable or USB cable, this transmits the complex valued waveform from MATLAB Simulink model to the transmit SDR. So this is the overall summary which we had already seen. Now there is an important question: do we need SDR in the initial phase of the design? That is the question. Do we always need SDR if you want to prototype a communication system, wireless communication system? So do we always need a TX SDR and RX SDR? Can we work without the TX SDR and RX SDR also at the initial level? And the answer is yes. How do we realize this thing? So if you look at the waveform ST and RT, so this waveform RT is received from the wireless propagation environment, and ST is the transmitted waveform, which may be your amplitude modulation or frequency modulation. But if you look at the waveform S tilde T and R tilde T, these are the complex waveforms. So if you abstract this TX SDR block, the real wireless propagation environment, and RX SDR block with an equivalent complex baseband representation of the channel, then you see that this whole thing can be represented by an equivalent complex baseband representation of the channel, which you can denote it by H tilde T. So during the initial phase, instead of connecting the models with TX SDR and transmitting the actual waveform, receiving it through the RX SDR, one can also introduce a complex equivalent baseband model of the channel, which actually abstracts the TX SDR, the real wireless channel, and the RX SDR, and directly you can generate the R tilde T from S tilde T using this equivalent channel S tilde T. And this is what most of us follow during the initial phase of our study. So if you want to simulate a system, if you want to analyze a system, you can start with the message signal MT, then you use your MATLAB model or Simulink model to generate the complex baseband equivalent of the signal, which is S tilde T, and then you can directly receive R tilde T, which is the simulated version of the actual R tilde T, by using a model of the channel, which is H tilde T. So H tilde T is an equivalent complex baseband representation of the channel, because R tilde T and S tilde T both are complex in nature. So H tilde T, which represents the equivalent baseband representation of the channel, is also complex in nature. And with this approach, you can still get R tilde T by using the model of the channel and design the overall communication system. So this is a very important approach, because most of our initial study, when we work on a communication system design, we work in the equivalent complex baseband domain, where we generate the complex signal and directly generate the received signal through the model of a channel. And typical model is complex Gaussian, where the real part and imaginary part is modeled using a complex, using Gaussian channels. So the real part is also Gaussian, imaginary part is also Gaussian. So the overall channel is complex Gaussian. So this is a very famous model for wireless channel representation. So such channel models are used for generating R tilde T, and then you can design the overall signal processing algorithms. The efficiency of your design depends on how efficiently you capture the behavior of the overall wireless channel in this H tilde T. Because remember, this H tilde T is the model of the channel. So the accuracy of the model will depend on how accurately you capture the behavior of the wireless propagation environment in this H tilde T. So with this, let us conclude this lecture. So after completing this course, once again, with the study of this lecture, I would like to summarize what are the learning objectives, although we have already discussed, but now we will be able to connect it better. After completing this course, you will be able to design MATLAB Simulink models for various communication systems. So that means, let's say you want to design a communication system for amplitude modulation or frequency modulation. That means you will be able to generate the model or the code in MATLAB or Simulink for corresponding to the amplitude modulation or frequency modulation waveform. And then you can connect this MATLAB Simulink model with the SDR hardware for the over-the-air transmission and reception. Then you can perform real-time baseband processing and waveform generation. So basically means that once you receive this baseband waveform R tilde t via SDR, you can perform the baseband signal processing in the MATLAB Simulink block running on your host computer. And you can analyze live TX-RX signals and visualize system performance. And finally, this enables you to implement a complete transceiver chain and validate the system performance, because you can transmit the message signal empty, and through this entire communication system chain, you will be able to recover the message signal empty back, which here we are representing as m hat t. Thank you everyone. So let's stop here and let's meet in the next lecture with some of the basic building blocks of digital signal processing and time frequency analysis. Thank you.